Hey, hi, this is Ajit. Welcome to Step by Step Data Science tutorial. So today we will write machine learning equation from scratch for logistic regression. So we will cover all sigmoid function, cost function, gradient descent, and we will all write these equations step by step in Jupyter Notebook. So let's start with logistic regression. So this is my library. So we know that logistic regression is a classification module and our output is discrete. Discrete means a whole number, either 0 or 1. Okay, so this is my data. This is the end-to-end machine learning course dataset that I have used. So this is my data. So this is the header. So we can see here like this one, the first column is our exam 1 score, the second one is exam 2 score, and third one is the output. 0 means based on exam 1 and exam 2 whether a student or a person is admitted in the university or not. This shows us the output. So if we see if we see our output, like suppose percent. So we have two outputs. So this is a binary classification module. So we have two outputs, right? So let's plot this data and let's cases for admit, not admit, and one case is for admit. So I will keep all my zeros in one variable and all ones in another variable, and I will do a visualization. So what I will be doing is I will be excluding all zeros in one and again all ones in another variable. So I will be splitting that so that I will be coloring dt of 2 will be equals 0. This will split my data and will show all zeros for exam 1 score. Exam 1 is my 0 and 2 is my third column, which is admit not admit. So this will filter out all the not admit data. Okay, so this is my all non-admit, we can see. Likewise, I will plot I will include all my non-admit data for exam 2 score. So this one is my exam 2 score. So let's write a function for that. Plot data dt. So as I said, I will be doing plot plt dot plot, and my first variable will be dt, and I will include all my first field on the condition that my df of second column is all equals 0. This will be my one axis. Another axis will be for all ones, and let's distinguish this with ax and label it with this is my all non-admitted. So if we plt dot legend, we need to see legends. If we do plt dot show, and if we call this particular color, so likewise we will highlight all or admit case with another color. Let's say make it another color by O, and this will be all my one admit cases equals 1 equals 1. So this is my another plot. So here we go. This is my admit and non-admit plot. So here we can clearly see that if we draw a line over here in the middle, then we can distinguish whether a student is admitted or not admitted in the university. Okay, so this is my data. So let's write a sigmoid function and hypothesis for logistic regression. know that in linear regression, my hypothesis as theta of x was theta transpose of x. So in logistic regression, if we take z of theta transpose of x, where my z is theta transpose of x, then my hypothesis as theta of x is 1 by 1 plus e to the power minus z. So why did we include this equation, this hypothesis? Because as we know, our logistic regression is a classification module and our output should range between 0 to 1. So my hypothesis should be less than equals to x of x less than equals to 1. It should be greater than 0 and less than equals to 1. So if we do exponential and take a sum and divide it by 1, then if we implement this equation, we will get our value that ranges between 0 to 1. So let's write this equation and do a visualization in Python. So I'm creating class here because in the next video we will be implementing regularization in linear regression, and we will be using the methods that we have created in a class. So instead of doing it repeatedly, so I thought of creating class and can inherit that class while implementing regularization in logistic regression. So let's create a class, logistic regression. Let's create our default constructor and initiate it with pass. Let's write another equation. This is my sigmoid. So my z would be my z theta. My z would be 1.0 divided by 1 plus np dot exp minus z. Let's call it theta. So let's return this. So this is my sigmoid equation. So this is my file. So I have already created a class. So let's create an object. Sigmoid class name. It's called Sigmoid. Let's give it another name. Equation. Let's give it vector sigmoid. Let's pass my value 0. So if we do 0, that would be, so how did we get 0.5 is here my if my z is 0, then my h theta of x is 1 by 1 plus e to the power 0. This means 1 by 1 plus 1, which is 1 by 2, which is 0.5. So my sigmoid function is working fine. So now let's do a visualization and for my sigmoid function. And so what I will be doing now is I will be visualizing my sigmoid function. So we know our h theta of x will be 1 by 1 plus e to the power minus z. So this is my y. So I will be plotting the sigmoid function, taking my range from -5 to 5 and applying that over z and plotting the x value. Okay, so finally I will plot this, and it would be something like this. This is my 0.5, this is my 1, and this is starting from 0. So my sigmoid function, if I do a visualization of this equation, it would look something like this. So let's visualize this equation. So what I will be doing is my x will be ranging from -5 to 5, and in y I will be applying this formula 1 by 1 plus to the power minus 4 minus 5 or 5 minus 4, so on, and then I will be doing a plot, which would look similar to this. So let's visualize my sigmoid function. So let's write a function sigmoid. I will be using, so my x will be, I'll be using np dot range -5 to 5, and say my variance is 0.1, and so my y will be this, the sigmoid function which I have implemented right now. So this will be my y. Let's do a plot of x comma y. This will be pld dot plot. So yeah, we can see that it's showing something similar to one that I have shown you. So let's add a boundary line in between that can distinguish my positive and the negative data. So what I will be doing now is I will be adding this line, so that it can distinguish, and I will be even plotting, writing annotation that shows the coordinate of this point, this point. Okay, so let's add some boundary line to make it more clear, so that we can have sigmoid function. So let's add and notate. So let's say it's 0 to 0.5. My xy will be 0, 0.5, and my position of xy text is something close to -2.8, say, and my y would be 0.55, suppose. So yeah, let's make it 3. So let's look a bit closer. Now let's add a boundary line. The x be vertical and horizontal we need to write. Let's include a horizontal line first. Horizontal line will be at y equals 0.5. Let's color it black, and let's include this with dotted line. Let's plot the similar way for my horizontal axis. Sorry, vertical axis. Vertical axis, my x will be 0. So we have a boundary line. Now this looks a bit clear. So this looks a bit more far away. So let's leave it -1. Yeah, now it's much better. So this is how we plot our sigmoid equation. So this is my boundary line, as I mentioned. So uh, anything above this is all positive value, and anything above beyond this is negative value. Is greater than or equals 0.5, then we predict our value for y will be our 1. So if our theta of x is less than 0.5, which is this, below x 0.5, 0.5, then our y is 0. So anything beyond 0.5, our y will be 1, and anything beyond less than 0.5, our y will be 0. So what we can interpret is, suppose if we do a sigmoid function, if we plot a sigmoid function for 0 point, let's say for 0.9, what we got, the sigmoid value for 0.9 is 0.71. What does this mean is, so for said like our if our h theta of x is 0.5, then we say like our y is 1. If our h theta of x is less than 0.5, our y is 0. So if it is greater than 0.5, then we say that our y is 1. So what does y equals 1 means? In our case, 1 is for admitted to university, and 0 means not admitted. So any probability of 0.71, 0.71 is our probability, and we can even say that s theta of x for the probability of y equals 1 given x parameterized by theta, the probability of having 1 is 0.71. So likewise, what would be the probability of not being admitted? So if s theta of x p for y equals 0 given x parameterized by theta, we can say this is for admitted. Not for not admitted, we can simply say that it should be 1 minus 0.71. So which is 1 minus probability of y equals 1 given x parameterized by theta. So finally what we can say that our probability of y equals 1 x parameterized by theta plus probability of y equals 0 of x parameterized by theta is whole equals 1. So we can say that, we can say this is equals to 1. So now let's implement our hypothesis. So right now we have implemented sigmoid, which is 1 by 1 plus e to the power minus z, and we know that our z is theta transpose of x. So our hypothesis will be 1 by 1 plus e to the power minus theta transpose of x. So let's implement this equation. Also keep in mind, regarding this equation, we will be implementing cost function based on this equation. So for now we will write hypothesis equation that calculates the given parameter theta and x. We will calculate this hypothesis. So one thing to note is that, as we said, for our hypothesis as theta of x is z of theta transpose of x, and we know that we have two feature. This would be our x naught, theta naught x naught plus x1 theta 1, sorry, theta 1 x1 plus theta 2 x2. Since we have two feature, this is my exam score, this is my exam score 1, score 2. So we need to implement this equation, which is a matrix multiplication of this and this, and then we need to take a sigmoid. This equation, we need to implement this equation. We have already written a function to implement this equation. Right now we need to include this equation. So we need to do this multiplication and then apply sigmoid function. So here we know that our x is again matrix of x naught, x1 and x2, and my x naught is all 1. So I will be writing a function that adds 1 in my original data. So again my feature will be, right now my x is 64.2, 65.2. This is for score 1, score 2. So I will be writing equation where my x will be appending 1, we will append 1, so that we can populate this equation 1 and our 64.2, 65.2, so on again 1, 24.5. So our x variable will be something like this, 34.5. So once we have this, will be our x again, and our theta will be again 0, comma 0, 0, 0. This would be for theta naught, this would be for theta 1, and this would be for theta 2. So we will be implementing again dot product of this, and once we have dot product of this, then we will dot product of x and theta, and once we have that, this would be our z, and then we will call sigmoid function. Hope this makes sense. So let's append 0 first. Append 0. Sorry, okay. So my x is 0, values, and y is 2 dot values. My m comma and m is my total number of rows, and n is the number of feature, will be x dot shape. X naught will be all ones. I've already told you. It will be all ones. Sorry, ones of all of m comma 1. And I need to append this with my x variable, x comma np dot append x comma x naught. X is equals 1, so that I can append it horizontally. I will return x comma y. So my x comma y will be 1. Bracket is missing here. So now if we look at x, it's been appended on last column. We need to append it on first. So change that. So yeah, we can see now x has been appended, and our initial theta, let's declare initial theta. So our initial theta is all zeros. Let's save my one. Now let's write a hypothesis for this equation in my class. So this is my sigmoid. Let's write a hypothesis. Hypothesis will accept x and theta. So as I said, it will be, we need to do dot multiplication, dot of x comma theta, and then we need to apply sigmoid. So my h theta will be sigmoid of theta. So we need to include self here, then return self theta. So I have already created an object. Let's dot, right? Our function name is hypothesis. It's method. So let's pass x comma initial theta. So spelling mistake. Sigmoid. Let's start on one hour. So here we see our hypothesis is 0.5. So what we did is, so we know that our s theta of x is z of theta naught x naught plus theta 1 x1 plus theta 2 x2, because we have two features, score 1, score 2, and this is again vector of 1. So we did a dot multiplication, which is matrix multiplication, and then we know that z is 1 by 1 plus e to the power minus z. Then we have applied this function. So and our initial theta was, this was 0 0 0. So our z would be, definitely will be 0. So 1 by 1 plus e to the power 0, which is 1 by 1 plus 1, which is 0.5. So that's what we have got. Our result is 0.5. So this is my hypothesis. That's simple. So we have written hypothesis, and now what we need to do is we need to write a cost function. So remember what I told you is probability of y equals 1 x parameterized by theta plus probability of y equals 0 x parameterized by theta is equals to 1. So one thing we need to note is the logistic regression follows Bernoulli's equation. So Bernoulli's equation also works same as logistic regression, where our output is binary. So if we look at Bernoulli's equation, what our equation says is, if x is equals to x, then my p of x and 1 minus p of 1 minus x, where p is probability and x is my input parameter. Input parameter. So if we have a binary output, let's say 0 1, for example, if we toss a coin, we have chances of getting head or tail. That also follows by Bernoulli's equation. So if we toss a coin, we have chances of getting head or tail, right? So let's say my head is 1 and tail is 0. So x equals head for 1. My equation will be p of 1 minus p of 0. Okay. If it is equals to tail, then we will get p of 0 1 minus p of 1 minus 1 minus 0 1, that equals 1 minus p. This is p, this means success, and it's like 1 minus p means failure. So why I am explaining to you regarding Bernoulli's equation is the logistic regression also work based on Bernoulli's equation, and our equation for Bernoulli's equation is x equals x p of x. This is our equation. Similar to this equation, in our logistic regression, this is our probability p, and this is our input variable. So we know our probability is given by s theta of x, and our input variable is y. So of so for y equals y, we can even write in this way, like s theta of y 1 minus h theta of x, or 1 minus y. So if our y is equals to 1 in this equation, if our y equals 1, what we get is s theta of x of 1 minus s theta of x. If our y is equals 1, then 1 minus 1, it will be s theta of x, y equals 1. If our y equals 0, then what we get is s theta of x power 0 1 minus s theta of x 1 minus 0, which is equals to 1 minus s theta of x. So this is what we initially came up with, which says like if given of y equals 1 plus y equals 0, our result is equals to 1. So we can write this equation. So we can write f of y, hope this is making sense to you all, s theta of x to the power y 1 minus s theta of x to the power 1 minus y. Now in order to generate a cost function, we need to calculate log likelihood. So this is what even we call it as a likelihood equation. So we need to calculate log likelihood. Log. Firstly, we need to calculate likelihood equation. Sorry. So my likelihood equation will be. So what is likelihood equation? Likelihood equation, if we take the product of all product of this equation, that would be my likelihood function. So my likelihood function will be product of, it's I ranging from 1 to m, product of yi given by xi parameterized by theta. So this will be equals to so dot of m I equals 1 s theta of x whole parameterized by I whole yi 1 minus s theta of x whole I parameterized by whole I to the power 1 minus y I. So if we're taking log, if we take log, then this equation will be log of s theta of x of I whole yi 1 minus s theta of x of I whole 1 minus yi. So we know that log e to the power a is equals a log e. We know this equation. Also log m times n is log m plus log n. So we need to keep this in our mind. So this will become, so this is my log, suppose this is e to the power a, and will become y of I log of s theta of x plus 1 minus y in 1 minus s theta of x. This is plus because it's m times n, this times this. So this is my log likelihood function, function. So we know that, so the cost function is our minus 1 by m times this equation. So minus 1 by m is similar to like last time we had a cost function when it ranges from 1 I to m, and we did my y minus s theta of x whole square. Instead of using this equation, we have used log likelihood right now. So that's why it's this is replaced by our this function y of I log of s theta of x plus 1 minus y 1 minus s theta of x. So this is our cost function. This is how we derive cost function. So we will visualize this equation. So one thing to note is why did we take log? You might have question like, why did we take log? Why didn't we use MSC that we did in linear regression? So I will explain you step by step. Like firstly, the reason for taking log is if we implement MSC this equation, then our plot will be something like this. So we need to have minimum cost function. So we need to have minimum value. So our local minimum will be this and this position, right? So we need to look for this value, which is our global minima. So implementing MSC will give us multiple local minima. So we cannot implement this equation and as we will not be getting global minima, and also this equation is considered as non-convex equation, non-convex equation, non-convex graph. So we need a convex graph that can give us the minimum cost function so that we can get optimal value of theta. So if we implement this equation, also another reason for, so this is the reason why we cannot use MSE equation. Another reason for using log is, one thing we need to note in our mind is, like, we have an equation which is exponential. So our equation is 1 by 1 plus e to the power minus theta transpose of x. So we need to take a logarithm so that we can get rid of exponential value. So one of the reasons for taking log is to get rid of theta, get rid of e exponential value. And if we take a log function, if we take a log equation for, suppose now for y equals 1, what would be our output? So our y equals 1, j theta would be minus 1 by m log of s theta of x. 1 minus 1 will be 0 for y equals 1. So let's exclude this one. Also, so if we plot this graph for y equals 1, so what we will get is something similar to this, like this. If we implement, if suppose our y is 0, then our j of theta will be 1 minus, here even we need to take, this is log of 1 minus s theta of x. So it will be 1 minus 0 of log of 1 minus h theta of x. So this would be my log of 1 minus h theta of x. So if we plot this, then we will get something like this. And if we combine both 0 and 1, then we will get our output something like this and this. This line is my y equals 0, this is for y equals 1, and we can get our, this will be our global minima. So let's visualize this plot in Jupyter Notebook. So what I will be doing now is, I will be visualizing the cost function by populating value either as y for y equals 0 and y equals 1. So what I will be taking a range of probability from 0 to 1 and doing I will do my visualization so that I can plot these two graphs. So my x will be, suppose, let's say this is my p, x is equals np dot, let's say my x is from 0 to 1 and interval is 0.01. Let's plot 1 point, velocity plot x comma times np dot log of x dot. So this will be my dot title. Let's give this as for y equals 1. So if we plot, then it would be something like this. And if we do it for So that's why we have -1 here, because if we multiply it by +1, then it would be something like this. And then minus, which is for 0. If we take positive of love, then if we plot both of our chart, then say, then here we will get a global maxima. That's why we did -1, so that we can get a global minima. That's the reason of doing minus, so that we can get a global minima. So this is the visualization for taking log for y equals 1 and y equals 0. Now we will write this equation in Python, and we will implement this equation. So let's write this equation. So this equation is, so what I will be doing now is, now my cost function j of theta is -1 by m sigma I equals 1 to n yi log of s theta of x plus 1 minus yi xi log of 1 minus s theta of x. So what I will be doing is, so I will be taking a matrix multiplication of, I will be doing matrix multiplication of this y times log of h of x. We have already calculated this. This is my hypothesis function, and we will take log of hypothesis function, and then we will do a dot product with respect to matrix multiplication with respect to y. And we already have this equation. We will do minus of 1, and we will take log, and we will implement this equation, and we will do a dot product of this. So if we do a dot product of this and this, it will automatically do the summation, and then we will finally divide it with m. M is our total number of rows. So let's implement this equation. So my cost function will be comma theta comma x comma y and n comma n will be my shape x dot shape my h theta will be self of this x comma theta. This is how we get h theta, and then compute j. J will be my np dot product of minus y times np of h theta minus np dot in dot product on 1 minus y comma lower 1 minus of theta. If you divide this with respect to m, you will get cost function. So let's return g. So this is my hypothesis for cost function, and the initial theta x and then y. Initial theta x and y. The np is missing. So we start another. So it's been successfully executed. So which is my cost. Let's check for another value of cost. Suppose my test theta is np dot, and suppose minus 24 comma 0.2 comma 0.2. So let's check. Okay, 2.69. So this is my initial data. 2.1. Yeah, this looks correct. So now we have implemented cost function. Now we will write gradient descent equation. So this is my cost function. We know that our gradient descent equation is theta of j, theta j plus alpha is my learning rate, and if we do d by d of derivative of j theta, we get cost function. So I will be proving the cost. I will be doing a mathematical equation. I will derive and prove gradient descent equation. So if we do a derivative of this equation, then we will get something like as theta of x minus y respect to x j. This is similar with similar equation that we got from linear equation. So if we do a derivative of this, we will get this equation. So let's do a derivative from scratch. So my j of theta is minus 1 by m sigma I equals 1 to m yi log of s theta of x plus respect to I 1 minus yi log of 1 minus s theta of x respect to I. So we know that our s theta of x is 1 by 1 plus to the power minus theta transpose of x. So this will be, if we substitute our value here, and this would be log of 1 by 1 plus to the power minus theta transpose of x. So this will be, we know that log of m by n is log m minus log n. So this will be my log 1 minus log of 1 plus e to the power minus theta transpose of x. So this will be, again this will be my 0, and lower constant is 0. So this then we will be remaining off with log 1 plus e to the power minus the transpose of x. Again, likewise for log of, now we are doing for this equation of 1 minus 1 by 1 plus e to the power minus transpose of x will be log of 1 plus e to the power minus theta transpose of x minus 1 divided by 1 plus e to the power minus theta transpose of x. This will be cancelled out. Then it will be remaining, it will be log of the power minus theta transpose of x by 1 plus e minus theta transpose of x. And we know that log of m by n is log n minus log n. This will be log e power minus theta transpose of x minus log of 1 plus to the power minus theta transpose of x. And again we know that log of e to the power a is a log e. So this will be, again this will be minus theta transpose of x with respect to I. This is all with respect to I, minus log of 1 plus power minus theta transpose of x with respect to I. So this is my second equation. So my final j of theta is, so my j of theta would be, so minus 1 by m sigma I equals 1 to m minus yi, and my log of e to the power log of, so log of my this equation I have derived it here. So this is minus log of would be minus log of 1 plus e to the power minus theta transpose of xi plus 1 minus yi of my log of 1 minus 1 of, so for this equation I have written, this is my equation. So this will be again minus theta transpose of xi minus log of 1 plus to the power minus theta transpose xi. So I equals 1 to m minus yi minus log of 1 plus e to the power minus theta transpose of x. Now let's open that. This will be again minus theta transpose of xi minus log of 1 plus e to the power minus theta transpose of xi. If you multiply 1 with this and then y with this, then minus plus, so y theta transpose of x minus plus, this is my initially plus y of log of 1 plus e to the power minus theta transpose of x. And so this and this will cancel out. So what will be remaining? J of theta will be minus 1 by m sigma I equals 1 to m minus theta transpose of x of I minus plus y theta transpose of x of I, so with respect to I, plus minus log of 1 plus to the power minus theta transpose x of I. Now again minus 1 by m sigma I equals 1 to m yi of theta t x of I minus theta t of x of I minus log of 1 plus to the power minus theta transpose x of I minus 1 by m I equals to 1 to m yi theta t of xi. If we take it again in logarithmic form, then it will be log of e to the power theta transpose of xi minus log of 1 plus e to the power theta transpose xi. We know that log of e to the power a is a log e. So this concept is being applied here. Then minus 1 by m sigma I equals 1 to m yi theta t xi. If we take minus common, and then it will be like m plus n, so log m plus n is equals to log mn. So if it will be, so we can simply write this as log of e to the power theta transpose of xi times 1 plus e to the power minus theta transpose of xi. So if we solve this equation, we will finally get minus 1 by m of y minus h theta of x with respect to I whole x I, and this will again be our 1 by h theta of xi minus y xi. So this will be my final equation. This is my gradient descent equation. So now let's implement this gradient descent equation. So what another function, if gradient, suppose let's say gradient, this would be my, we need x, y, theta, and let's say h theta will be from here, and my gradient descent will be h theta minus x minus y, sorry, and private matrix multiplication with respect to x, and then finally divided by m. So this is my gradient descent equation. So So let's call this in Jupyter Notebook. This is start and run on kernel. So this will be my gradient. My equation name is gradient theta x. So my parameter is x, y, and theta. So let's take a test theta and run. Let's take our output. So this looks good. So this is the gradient descent for if we take our theta as this theta. This is our if we use our theta as minus 24, 0.2, and 0.2, then we get this gradient descent equation. So now we are going to use in gradient descent. We have to choose theta, and we need to do a iteration to calculate optimal value of theta. So if we use f mean function of psi pi, this will give us the optimized value of theta. So this is the advanced optimization and method. If we implement f mean of psi pi, we will get the optimized value of our theta, and that would be our optimal value. So let's implement that function. So this is needed to get optimal value of theta. So let's implement that minimum cost, so we can get a minimum cost. Let's calculate, give a equation name minimum cost, and this would be my again cost function. Theta x, y, f min, and our function is this one, cost function, self dot function. Our initial theta x0 is equals to theta, and our arguments is comma initial. So let's call this equation. So our theta will be, we have our object rig dot, our function name is minimum cost. We need to pass this cost, comma initial theta x, and our initial theta is this. So if you look at theta, this is our final value of theta. So why did we use this function? Is because this gives us the more optimized value of theta. Instead of using gradient descent this equation, this would give us a more optimized value. And we also don't have any issues like in gradient descent we need to specify alpha, and we need to look for many iteration. need to iterate and get optimal value. So if we implement SciPy library for this, we get optimum value of theta without taking hassle of using alpha. So this is the more optimized way of calculating in theta using a SciPy library. Okay, I think that makes sense. Now let's do a prediction. So this one. So my sigmoid function something looks like this. So if we get a hypothesis of x, if that is greater than equals to 0.5, then our y is 1. So and if our s theta of x is less than 0.5, then our y is 0. So we need to implement this equation so that we can get output as y equals 1 and y equals 0. So let's write a function to do that. So initially I will declare a function that does the calculation. Self comma x. So in x I will write where if my x is less than 0.5, then that should be 0 or 1. It should be my one equation. Then I will return x. Again I will write another function which should be for prediction. So my predict would be self comma x comma theta. So first I need to get my hypothesis. This would be similar to this. And my output will be get my result, and then I will apply all the logic that says if my hypothesis is less than 0.5, this will be 0 or 1. So my y period again will be simple. So the y period. So this will give my output as 0 or 1. So let's rerun. So my regression is this. So this dot predict. So my y period anyway dot predict. I need to pass x and theta. So here is my prediction. Now let's calculate accuracy. Accuracy is simply taking the mean of my output and predicted output. So my accuracy will be, so let's say score self dot y comma self content comma y trade. So my accuracy will be mp dot mean, simply mean of y equals y trade. Newton score. So let's rerun this. So again my accuracy score will be this dot score bracket y comma 100. You can see my accuracy is 89%. So now let's verify this with scikit-learn logistic regression module. So this is my module and this is my x and y parameter. I'm doing fit and then calculating score. So it's 89%, so it's matching with what we have implemented. So now we will be doing a plot of uh, of what we have predicted. So this would be plotting our decision boundary. So what we know is, to distinguish this as negative and positive, our boundary value is 0.5. So we know that 1 by 1 plus e to the power minus theta transpose of x is equals to 0.5. So this would be our boundary line when if this would be 0, then if this value will be equals to 0, then 1 by 1 plus the power 0, this would give 0.5. So my theta transpose of x is, if this is equals to 0, then we can easily calculate our boundary line. What does boundary line means is, this one is admitted. So this is the plot that we have received earlier. This one is for score 1 and one is for score for true. So now we will be plotting our decision boundary, which means we'll be adding a line over here. This would be my boundary line. This distinguishes whether my value is, whether we predict our value as admit or not admit. So we will be adding a boundary line here. So how we can add a boundary line is we know that to separate a value of 0.5, for value anything greater than equals to 0.5, our value is positive, and if for anything less than 0.5, our value is negative. So our boundary line is y equals 0.5. So to be y equals 0.5, that is e to the power of 0, which is equals to 1, our this equation needs to be 0, right? So theta of transpose of x needs to be 0, which means theta naught plus theta 1 of x1 plus theta 2 of x2 needs to be 0. So one dimension is already, we know that x1, we can plot here x1, and another will be my x2, which would be my x2 will be theta naught minus theta 1 of x1 minus divided by theta 2. So this would be my another equation. So I will be implementing one equation this, and my another, so this would be my y variable x2. So I will be implementing this equation. So to get this boundary line x2, my x matrix will be max of this and this point, and my x2 will be this equation. So let's implement this equation and see our boundary line. So my x and y plot, this will be my y plot, and my x will be, so let's say my plot of x will be np dot array. This would be dt1 dot min comma dt1 dot max. So what we do this is, so that we can get minimum and maximum value for x would be, so my x minimum would be somewhere here. So this would be max minimum. My y maximum will be here, so that I can get this point, and then if I implement this equation by plotting my value of x1, we can get a decision boundary line. So let's implement that. So my y would be lot of y would be minus theta of 0 plus theta of 1 times lot of x square y to be divided by theta of 2. So let's check if this is working or not. Yeah, it's working. Now we already have plotted our x and y. We have already explored x and y. So let's add one more plot. Let's repeat my x and y. Let's say separated by r. Let's label this and extension. This is my let's add the legend. So this is my boundary line. So if we implement this equation, then we can get our boundary line. So let's check one equation. Suppose that if we do a plot and if you add 55 comma 85, suppose if you add that in, let's say that is shown by rx, and ms is d. So 55 comma 85 is this position. This 55 is for score exam score 1, and this one is for exam score 2. So if it's exam score 1 is 55 and exam score 2 is 85, this then we can say that this is admitted. So this person is admitted in the university. So if we do our annotation, if we let's say let's annotate this. This one, 85. So this is one point. Let's okay, where are we include it? This is my so this is my point. So this is where we say if a person has a score of 55 in exam 1 and score of 85 in exam 2, then a person is admitted. And let's check the probability, like how much probability do we get. So it will be my rig dot sigmoid. We will need to do np dot product of 55 comma 85, with respect to theta. We have our theta value. Let's keep it the same. Probability. Okay, so admission probability for score 55 comma 85 is equals to probability. So this is in so so this we can say this is admitted because it falls under admit zone and the probability is 96%. So here comes to the end of my lecture. So we have covered a lot of topic. Hope you like my video, and please subscribe and encourage me to post more videos. Thank you so much.